Hello, everyone, and welcome to the U.S. Geological Survey's virtual public lecture series. My name is William Seelig, and I will be your host and moderator today. Before we introduce our speaker tonight, I have a few announcements to make. For next month's lecture, we have Carolyn Dreger, who is a USGS hydrologist. Carolyn will be giving a talk on Mount St. Helens called Lives Changed, Lessons Learned, and Legacies of 1980. That talk will be on Thursday, June 24th at 7 p.m. Pacific. So make sure to mark that in your calendars. And just a few quick tips on how to turn on a couple of features using our streaming platform. To turn on the closed captioning on your desktop, you can do so by clicking the gear-shaped icon, which is located on the upper right-hand corner of your screen. And closed captions on your mobile device can be turned on by tapping the phone and clicking on the closed caption TV icon, which is located at the bottom right-hand corner of your screen. Toward the end of the lecture, we will open it up to the question and answer session. If you have a question for the speaker, you can submit them through the Q&A chat window. And to find the Q&A chat window, I'll look for the question mark icon on the upper right-hand corner of your screen. That will bring out the Q&A panel where you can type in your question. If you're on a mobile device, you can click on the question mark icon, which is located on the upper right-hand corner of the screen, and submit your question in the Ask a Question field box. Please understand that we may not have time to answer all questions that come through. We appreciate your understanding in advance. Now for the exciting part. So to introduce our speaker. So tonight we have Austin Elliott, who will be discussing recent fault ruptures in the Western United States. Austin received his bachelor's in earth sciences at the University of Southern California. He then received his PhD from UC Davis, where he researched from a geological perspective how earthquake ruptures are arrested along a fault system. After that, he spent 5 years in the UK working on in postdoc research position with the Center for Observation and Modeling of Earthquakes, Volcanoes, and Tectonics at the University of Oxford, where he studied large, early, and pre-20th century earthquakes in Central Asia, which is one of the highest seismic hazard regions in the world. Austin's first stint with USGS was actually in 2003 as a high school intern, where he was given the opportunity to find and analyze accounts of 19th century earthquakes in old archival newspaper film records. More recently, he joined the USGS in 2019 as a research geologist, where he studies the record of earthquakes in the landscape at the Earthquake Science Center in Moffett Field, California. And now I'm going to turn the mic over to Austin. Austin, the floor is all yours now.
All right, thank you very much. Let's get us started here. Hi, everyone. Thanks for having me, and thank you for taking the time to watch this talk about what we've learned from recent earthquakes in the Western US. As Will said, I work in the Earthquake Geology Project at the USGS Earthquake Science Center at Moffett Field. This means that I study the impact, effects, and record of earthquakes in the rocks, the geology. So let's familiarize ourselves with the recent earthquakes that I'll be talking about. While there were a whole host of traumatic things piling up at once last year, you may or may not have noticed that earthquakes did not stop bothering us while we dealt with the devastating impacts of a global pandemic. Not long after the US cities began to shut down, Salt Lake City was rattled by a magnitude 5.7 earthquake. Scarcely 2 weeks after that, a much larger earthquake emanated from the remote mountains of Idaho, shaking many of those same folks and more. The onslaught continued with a large earthquake in near Bodie Ghost Town in the Eastern Sierra of California. And as we were watching that notable sequence unfold, the widely felt magnitude 6.5 Monte Cristo Range earthquake occurred near Mina in remote western Nevada. Just over a month after that, magnitude 5.8 earthquake struck beneath Owens Lake bed, also in the Eastern Sierra. And aftershocks from the largest of these earthquakes continued that whole time. Then in August, North Carolina joined the party with a widely felt earthquake of magnitude 5.1. As succinctly stated on the Twitter by the US Consumer Product Safety Commission at the end of April 2020, there was a lot going on. This may seem like an inordinate number of earthquakes, but if we take a bigger picture perspective of the active Western US, we see that it's not really abnormal at all for the place to be lighting up with earthquakes. Here, we're watching a fantastic animation by NOAA, specifically the Pacific Tsunami Warning Center, whose purview does include earthquakes as well, speeding us through 4 decades of earthquake occurrence measured across the US. As the animation continues, it shows that moderate to strong earthquakes are indeed quite common across the Western US. Only a few of them make history when they strike near population centers. Many are long forgotten because the Western US is largely wide open, sparsely populated space. The animation continues for a while, and I recommend that you search for NOAA 40 years of earthquakes on YouTube to continue watching this pretty spectacular animation. The most recent of these large but soon forgotten earthquakes occurred just a year ago this month. Its anniversary is the occasion for which I'm invited to speak to you today. That earthquake was on May 15th, 2020 at 4 in the morning, was a magnitude 6.5 so-called Monte Cristo range earthquake because of where its epicenter was. Although the earthquake was widely reported as felt, as shown here in this USGS shake map, which contains, as well as instrumental records, did you feel it reports from the online submission system that allows you to report the shaking experience that you had. The areas with the strongest shaking were actually some of the least populated areas in the entire country, as shown here in this USGS pager system's population exposure map. Pretty much the only impacts from this earthquake were to the tarmac and roadbed on Nevada State Highway 95. It's shown in this picture from the Esmeralda County Sheriff. While only this one of the Western US earthquakes during the year of the pandemic ended up large enough to break faults to the surface and study geologically, the prior year saw 2 surface rupturing earthquakes in Eastern California, which were widely felt across the southwestern US. At about 10:30 a.m. on the 4th of July 2019, folks preparing their barbecues from LA to Las Vegas were jostled by the long rolling waves of a distant magnitude 6.4 earthquake, which was centered near the city of Ridgecrest. Being so large, it was the immediate target of scientific investigation, and a host of seismologists and engineers descended on the badly shaken town of Ridgecrest to begin to study. Literally just as they were wrapping up their first day of reconnaissance on the 5th of July, a much larger magnitude 7.1 earthquake struck. You can see the difference in scale and impacts here between these 2 images. Some of my colleagues were caught on camera as they broke their wrap-up huddle just as the larger quake began. What you're looking at is closed-circuit television captured from a hotel in Ridgecrest, where scientists had gathered to stay the night as they studied the impacts of this earthquake. They've just wrapped up a day of talking about what they've seen, what their plans are, and they're ready to head and probably go to either dinner or bed as they wrap up here. As Sean closes the door of his car, he seems to trigger the earthquake. The shaking that you see here ends up being quite dramatic. There are a few things to notice. The earthquake lasts many seconds. This is characteristic of a very large earthquake, a magnitude 7.1. The shaking you'll experience is somewhere 20 to 30 seconds plus. The ground motions are very strong, but the buildings are nice and sturdy. They stand up. There are some panicked reactions, people running around outside of their buildings. The recommendation is, of course, to drop under sturdy furniture where you are, because running around risks tripping, falling, being hit by things. Nonetheless, these are understandable reactions to a really jarring event, especially after they've already had one. So this bunch of earthquakes out in the desert. I thought the San Andreas was our most famous threat. In shaking potential maps like this one prepared by the California Geological Survey, the San Andreas is indeed the hot spot, or the hot line. It carves an ominous gash through the landscape of coastal California, as pictured here, where it runs midway between San Luis Obispo and Bakersfield. But all of these recent earthquakes that I've mentioned, and others, which I'll talk about, have happened away from the San Andreas, over in the interior desert. Despite the San Andreas being the fastest moving and hosting the largest earthquakes, the fault has not ruptured in quakes since 1906 in the north, 1857 in Southern California, and even earlier at its farthest southern end near the Salton Sea. So all of these other earthquakes that we know about and have heard about in our lives in California have happened elsewhere in the state or in neighboring Nevada. So what gives? Furthermore, the San Andreas plate boundary is a simple fault. The recent fault ruptures elsewhere, some involve 2 to 5 faults, some involve 3 or more. The Ridgecrest earthquakes involved a huge host of faults, were not simple. Each of these recent complex earthquakes and many other recent well-imaged earthquake fault ruptures have been considered by scientists unexpected or surprising in their complexity. So why were we caught off guard by these? I'll expand the question further to, were we actually caught off guard? Or did we really have a fair idea that these would happen? Are these earthquakes really a surprise to us? Well, it's essentially part of our job as the US Geological Survey to answer these questions. This document outlines the USGS Natural Hazards Science Strategy. The mission of the USGS in natural hazards is to develop and apply hazard science to protect the nation, protect the safety, security, and economic well-being of the nation. To fulfill its mission and meet statutory responsibilities, the USGS must conduct geologic mapping and acquisition of geophysical data to enable a better understanding of hazardous processes, including sources and impacts, collect ephemeral data during hazardous events that will support future research to reduce loss, and develop long-term chronologies with associated magnitudes of hazardous events. I'm reporting on these as specific to earthquakes, but you can imagine that these apply to any number of the natural hazards that our country faces. A strategy document that was assembled by the constitutive agencies of the National Earthquake Hazards Reduction Program makes clearer what role the USGS science investigations play in understanding earthquakes. USGS has the statutory responsibility and authority to conduct post-earthquake investigations in order to provide insight into how faults rupture, understand and predict shaking and ground deformation, and document and improve performance of the built environment. I'm going to talk about how these earthquakes apply to all of these things. After the puzzling observations posed earlier about complex earthquakes away from the main plate boundary, you might be asking yourself, like my colleague Chad here, looking lost among the fault lines in the Nevada desert, what do we learn from mapping all these fractures? Why do so many large earthquakes keep happening outside that map zone of highest shaking probability? And how have recent earthquakes informed our expectations of future seismic events? This is what we'll be talking about for the next half hour or so. I've already spoken about our most recent earthquakes. Before we go much further, we're going to need to back way up and make sure that the relationship between earthquakes and fault lines is clear. You've already heard me, and you'll hear me more, using the words earthquake, fault, and rupture a lot during the next half hour, and I want to make sure that we're all on the same page about what I'm talking about. The remainder of the talk will explore some of the complex examples I highlighted to really see where mapping gets us, culminating with a report on the earthquake that happened just a year ago. So let's jump back to the basics of geology on Earth, the tectonic plates, pieces of the broken up hard shell of crust that surrounds Earth's hotter interior. The boundaries between these plates are where earthquakes and volcanoes occur as they grind against each other. The boundaries between the plates look like, well, in our case, the San Andreas Fault. But there's more to it than that. While the San Andreas runs up the spine of California, as pictured in this astronaut photo from the International Space Station, tectonic disruption of our crust extends far, far inland from that. thousands of miles even, where we still have tectonic action splitting up our mountain ranges. All that topography isn't just there for nothing. In fact, the reason we have tectonic activity so far inland is illustrated nicely by this animation of plate boundary evolution since 38 million years ago, constructed by Tanya Atwater of UC Santa Barbara with constraints from geological data. As the Farallon plate disappears beneath North America, convergence at the plate boundary stops, and the margin of the North American continent begins spreading back out into the space that's opened as the Pacific plate slides northwestward. The effect of this is to essentially open up and create the entire state of Nevada, among other areas. These days, we can actually track this motion in real time, which is astonishingly cool. An array of GPS antennae installed across the western US continuously reads out their positions to millimeter accuracy, tracking where they are and where they're headed, mounted firmly in the crust. This map shows their velocities. From these data, scientists can calculate the rate at which the crust is deforming, displayed here in map view. Does this look familiar? It's a lot like the seismic hazard map, and this is no coincidence. The deforming of the crust can also be seen directly in the terrain of the western states. Northward relative motion of the Pacific plate grinds these northwest aligned linear grooves in the mountain ranges of coastal California. The extension of the crust inland breaks up Nevada into its famous basin and range topography. Much of the terrain can be attributed to faults, the breaks in the crust which periodically slip to cause earthquakes. The USGS maintains a database of geological faults and their associated folds, in particular, the ones that demonstrate evidence of deformation in large earthquakes during the past 1.6 million years, the Quaternary period of geologic time. The Q faults database contains information on the recency of slip and the frequency of and the frequency of recurrence of movement in seismic events along these faults. This data forms the basis of our seismic hazard maps, which I'll get to in a moment. Because it involves the recency of motion on the faults, it's also a great way to image earthquakes that have in fact occurred and been measured in the recorded historical period, or since about 1850. But wait, earlier we saw earthquakes as blinking dots. Usually you see them as dots on a map. But here we have all these big red lines mapped out along the faults. So what exactly is the relationship between an earthquake and a fault? This is pretty key to the rest of what I'm going to talk about. Faults, as I've hinted, are breaks in the Earth's crust along which the opposite sides slip in opposite directions. They're usually stuck shut by weight and friction, but eventually tectonic forces overcome that and force them to lurch into a new position where they continue loading to lurch again. But the whole fault doesn't slip at once. It breaks as a growing crack, like you might see in your windshield. That crack nucleates somewhere beneath the quake's epicenter and begins to unzip the sides of the fault across a growing area. That area grows in either direction at about 1 to 3 kilometers per second. That's like 5,000 miles an hour, but the process only takes a few seconds. The fundamental thing that controls the magnitude of an earthquake is how much of that fault slips in one of these failures before stopping. This is crucial to how we understand and interpret earthquake geology. So, how do earthquake magnitudes then correlate to that total area of a fault that slips? Recall that the earthquake magnitude scale is logarithmic. That means that each unit increase from 0 to 1, 1 to 2, 2 to 3, is actually a 10-fold increase in the size of the earthquake. Metric units thus make for an easy and natural way to understand increasing fault rupture size with earthquake magnitude. And thankfully, I have some handy comparisons for you. So we begin with a magnitude 0 earthquake. You've probably never heard of these. These are generally not perceptible by humans. They produce very small ground motions and are only detectable in mines or places where you have really sensitive instruments right next to the source of the earthquake. A magnitude 0 earthquake is produced by about 100 square meter patch of a fault slipping. That's 10 meters on a side, or about the size of a typical apartment. A magnitude 1 earthquake, also way too small generally too small for people to feel, is the rupture of a portion of a fault that's about 30 by 30 meters on a side. That's approximately the area of a typical US home lot. In this case, what we're looking at is maybe 15 by 45 meters, but it balances out to give you 1,000 square meter area of a patch of the fault. A magnitude 2 earthquake, now we're getting into ones that you might notice or would be perceptible to humans. They're caused by a 100 by 100 meter patch of a fault rupturing and slipping at once. 100 meters should be familiar to everyone as the length, more or less, of a football field. 100 by 100 meters is maybe technically 2 football fields side to side, but we're only talking rough numbers here. So next magnitude up, a magnitude 3, that starts to rattle you. It's 300 by 300 meters. That's something like a long city block in America. A magnitude 4 earthquake, this one you're really starting to feel the shaking. It makes sounds. These are a 1 square kilometer patch of a fault, roughly, rupturing and slipping. That emanates seismic waves. That is roughly the size of a neighborhood or subdivision. In America, we're square miles rather than square kilometers, but we're talking ballpark numbers here. Magnitude 5 earthquake is a 10 square kilometer area. That's approximately the footprint of an international airport. So you imagine the footprint of LAX flipped on its side, sitting in the crust beside you. That's how much of the fault unzips to produce a magnitude 5 earthquake. A magnitude 6 earthquake, 10 kilometers on the side, well, that's the size of the whole city of San Francisco. Something important happens above a magnitude 6. The brittle part of Earth's crust is only about 12 kilometers deep or so. Below that, the Earth gets warmer, and the rock, like a too warm chocolate bar, bends instead of breaks, so it doesn't support the strong, rigid seismic energy that creates the earthquake. Once a rupture's diameter reaches 10 or 12 kilometers, it's broken the entire depth of the crispy part of the shell, and like a crack in your windshield, it begins to propagate just laterally to the side. This is when ruptures are large enough to break the surface and faults become expressed in the landscape. Here's what that looks like. Robert Wallace, an influential earthquake geologist for decades within the survey, summarized the landforms produced by horizontal motion along a so-called strike-slip fault. There's no quiz on this for you, but what's important to note is that there are a variety of distinct features that are diagnostic of a tectonic fault sculpting the landscape. There's this perpetual competition between tectonic disruption of the topography and rain and erosion wearing it down. But the eroded features themselves also form markers that we can track over time as they're offset by faults. Here's what these look like in real life, as seen from satellites orbiting our planet. Any of these are visible to you on virtual tours via imagery in your favorite mapping app. Just find a fault map and follow it to your favorite corner of the world. What you mainly see here is landscapes carved or deposited by water, gullies, stream channels, and big fans of deposited gravel, like this, which have been sliced and slid by lateral motion along the faults. You can see the faults slicing through each of these individual images, very unnatural looking straight lines. In this case, it's very conspicuous how they've shifted the deposits from the mouths of these canyons off to the left here. These landforms can be preserved for tens of millennia in desert environments, and they are fundamentally what we use to measure earthquake size and recurrence rate from the history of ancient earthquakes. This final one here is a geotourist destination in Carrizo Plain National Monument in Central California. It's a great stop for you on a future spring wildflower tour in the state. The offset and abandoned stream channels across the fault here are actually named for Wallace, the infamous prior figure. This is what the formation of one of these landforms looks like as a result of a single earthquake. You're seeing before and satellite images of the 2019 Ridgecrest earthquake in the Mojave Desert. These GIFs were put together by Sotiris Volkaniotis from which he posted on Twitter, but these are representative of the types of imagery that we look at and that we use to map out where these fault ruptures happened. Here's another example. In this one, you can see how the stream channel in the center is offset and may preserve evidence of this horizontal fault motion. Another view shows how these offsets impact anything built across them. In this case, roads. In this case, pipelines. This one is for water. Handling these unavoidable infrastructure crossings of active faults appropriately is one of the principal economic and safety motivations for detailed mapping of fault zones. A more dramatic example of faulted infrastructure comes from Palu, Indonesia, after the magnitude 7.8 earthquake they had in late 2018. You can clearly see what a hazard not just the shaking from earthquakes represents, but from the fault motion itself. California has many faults underlying its cities and has implemented laws requiring setback zones for large human-occupied structures. Plenty of things built before 1972, however, and some after, still straddle our fault lines. So if those last images weren't compelling enough evidence that there's a need to map and measure faults, it's important to know that the location and relative activity of faults represent fundamental elements of our modern seismic hazard assessments, which the US updates every 5 years with ever more and ever newer information curated by the USGS. Information such as the location of faults, possible earthquake size, the recurrence interval of those earthquakes, how often will a fault continue to produce those, different rates of slip recurrence, or the amount of slip in an earthquake, imply different sized earthquakes at different time intervals. And it's important to capture that information so that we understand the scope of earthquakes that may happen in the future along a given fault. We seek to understand the distribution of those recurrence intervals along our entire fault system, as well as how large, how long are the earthquakes that have, can, or will occur. Our principal information about what types of earthquakes may occur is what the earthquake ruptures are like that have occurred. Unfortunately, earthquake scientists rarely get to choose when to set up and conduct our experiments. We have to wait on the whim of nature. In California and Nevada, we have a pretty decent and fascinating record. And despite a few key notorious events in history, the Northridge earthquake, Loma Prieta, Silmar, so many of them have occurred in the remote desert that we've gotten lots of information without too much impact to society. At least 24 earthquakes since 1850 have ruptured the surface, allowing us to measure them. And these are just the biggest. Let's look at one such example, a Southern California classic, at least among earthquake scientists, the 1992 Landers earthquake. When this earthquake happened at about 5 in the morning, it left a 70-kilometer long gash through the desert. That's about 50 miles. You can still see evidence of the tectonic motions today, shearing the built environment. If you're ever visiting Joshua Tree National Park, a short excursion northward takes you to the land offset by the 1992 earthquake. You can see these things yourself, although looking on Google Earth recently, I discovered that this road has been repaved, maybe smoothing over some of the offsets. The far field should still be visible and is evidence of ongoing active deformation of our plate boundary. In the era when that earthquake occurred, 1992, scientists generally relied on a basic concept that the length of a mapped fault translated to the likely maximum magnitude of an earthquake that it could produce, sort of like using that table I showed you a few slides back. In 1990, a pair of researchers published a definitive paper summarizing the recognized active faults throughout the Mojave Desert, coining it the Eastern California Shear Zone. Here's the state of knowledge of the Mojave Desert active faults at the time of the Landers earthquake. If you travel between Los Angeles and Las Vegas, you pass over a regular succession of active faults. These have been the source of many of Southern California's large rolling earthquakes in the last few decades. Two important passages from this paper stand out. Number one, the Eastern California shear zone, because of its probable physical connection to the San Andreas fault system, may have accommodated a significant portion of the Pacific North American transform motion. These days, we know this to be true. We measure it with those GPS monuments that I showed you earlier, and we've had subsequent earthquakes that validate this claim. Another passage highlights the fact that the faults that have been identified here in 1990 are discontinuous. None of them are too long. Only one really appears to straddle the entire Mojave Desert. This passage implicitly suggests that the individual faults will produce limited earthquake magnitudes, at least compared to the long, straight San Andreas fault, which is seen on the lower left of this map. Then, 2 years later, the Landers earthquake struck. Here's the pattern of surface ruptures as mapped by whole teams of researchers from universities and government agencies. You can see that it involves more than one of these discrete faults. That was a wake-up call and remained the poster child of an unexpectedly multi-fault rupture. But what you can also see is that only small portions of it were previously unrecognized. Scientists had actually done a great job identifying the complete lengths of the active faults along which this earthquake rupture propagated. Notably, 7 years later, another earthquake, tangentially the first one that I ever experienced as a new transplant to California, unzipped along a couple of adjacent faults. While the smaller and less complex earthquake, the Hector mine again illustrated that we need to work harder on constraining how propagating earthquake ruptures navigate a fault system. Which branch do they take? How far can it connect adjacent faults across an apparent gap? Are the gaps between these faults real, or are they artifacts in our maps of high sedimentation rates burying the faults from our view? It takes a lot of different approaches and tools to answer these questions, and in the time since, we've made great progress. Here's the current Quaternary fault map for Southern California. The newest generation of seismic hazard analyses takes into account rules about how far between disconnected fault tips a propagating earthquake rupture can jump. These rules are based on observations, such as those from the Landers earthquake, but also on physics-based computer simulations and also laboratory experiments in small-scale analog sandbox models. Every new earthquake that we measure helps us hone the expectations for how earthquakes may propagate along the fault system in the future. The next example of an unexpectedly complex earthquake rupture came from just south of the border. The rupture actually spanned the US-Mexico border on the afternoon of Easter Sunday 2010. The so-called El Mayor Cucapá earthquake, named for the mountain range and indigenous land in which it occurred, ripped through the desert, forming these massive scars. Cars and swimming pools rocked and rolled across Southern California and northern Baja, while this rupture propagated along a set of 11 different faults. In an intriguing parallel to the Landers earthquake almost 2 decades prior, 2 researchers had published a paper just the year before documenting faults throughout the area and describing how they might operate or link together during a large earthquake. Here's that fault mapping in the area at the time of the earthquake. I want to highlight that the black lines in this represent fault lines mapped throughout the bedrock, and the paper described how they may be activated together above a low-angle fault below. Here are the faults that broke to the surface in the 2010 earthquake. A whole host of us mapped, surveyed, and measured this rupture, and it turns out that the way it operated was almost exactly as described that it might in John Fletcher and Ronald Spells' paper from just the year before, talking about other faults in the region. So despite the apparent physical complexity of all these faults linking together in a single coseismic rupture, the prior tectonic mapping had already recognized how this might occur. The rupture was unique, yeah, but was it wholly unexpected? In hindsight, no. Next, we moved to Southern California's most recent pair of large earthquakes, the 4th of July weekend 2019 Ridgecrest sequence that I mentioned earlier. You're seeing a video of the aftershock sequence that accompanied the 2 largest main shocks of the sequence. Aftershocks are just more earthquakes. responding to the dramatic, abrupt changes in stress introduced by a larger event. Importantly, they happen very near to the fault that ruptured, so they can be used to illuminate its length and location. As you watch all the recorded aftershocks light up this intersecting array of faults that slipped, you may recognize the same old story playing out. These earthquakes ruptured more faults than we might have expected, and in an unforeseen configuration. But we've gotten wise to these seismic tricks, and we've developed better ways now of assessing just how unexpected these events really were, so that we can try and incorporate their observed behavior into future seismic hazard models. Here are some of the striking examples of rupture through the Mojave Desert, at this point becoming familiar to you. Among the scientists that you see measuring the amount that these faults slipped are a group of my colleagues that embarked on a study of the ridge-crest earthquakes to quantify just how, quote-unquote, unexpected these ruptures were. Did we really know about these faults? Their work after the ridge-crest earthquake evaluated how much of the 2019 ruptures were or could have been known beforehand. What you're looking at here is the state of the Quaternary faults database before the ridge-crest earthquakes happened. What's shown here are the faults that ruptured during those earthquakes in 2019. About 35% of the faults that ruptured in 2019 were in fact represented in the Quaternary fault and fold database, but you can see that a number of them aren't. Nonetheless, lots of faults were mapped throughout this area prior to the 2019 earthquakes. What was unclear was just exactly how they might all link up together to produce a larger earthquake. To dig into this deeper and really show some results, what you're seeing in the map here is essentially showing you how much of, in the thick bold lines, showing you how much of the ridge-crest 2019 ruptures had been recognized previously in orange and yellow. The black ruptures are all ones that were sort of newly discovered. However, my colleagues looked through satellite images, air photos, and high-resolution digital elevation maps from before the 2019 ruptures to try and identify whether these faults could have been detected and had just been missed in compilation for the Quaternary fault database. They found examples like this, where the red coseismic rupture runs along a step in the landscape that is in fact an uplifted surface that's pretty clear tectonic evidence of tectonic activity. Sure enough, the 2019 rupture, though it may be difficult to see on this slide, shows up right in front of this step, about where we would expect it to form in a continuously active fault. In the end, what my colleagues identified is that something around 70% of the rupture was actually identifiable beforehand, not just the 35% that was in the Q-faults database. That's actually pretty good, and it underscores the continued importance of hunting for ancient fault scarps hiding in the desert. As you can see here, there are hundreds of them, and they're scattered across an area that is tens to hundreds of kilometers wide, maybe even thousands when you count the whole desert. So investigating each one of these scarps is a massive project to understand how they contribute to the seismic hazard. This brings us to our most recent surface rupturing earthquake, for which I led the USGS field response in cooperation with the Nevada Bureau of Mines and Geology, the California Geological Survey, and a host of academic and industry partners. Recall our tectonic setting: plate boundary shear over to the west, continental extension in the northeast. Here's where the quake's epicenter sits for context with regional tectonics and other historical events. Field teams were deployed to map the ruptures, to set up temporary seismometers and GPS stations, and to document any damage. Mobilization at that point required strict establishment of and adherence to COVID safety protocols. We were early in the pandemic. That made it a challenge, but the Nevada teams arrived in the field the day of the earthquake, and most of the teams from California arrived the following day. When we got there, we found ample evidence of the strong shaking near the epicenter. Most notably, these toppled rocks. You can see the path coming down the hillside here where the rock jumped, bounced, left divots, and then split open as it landed at the bottom. And here, this boulder that rolled down, leaving a long trail through the sand. We were also greeted by a pretty vigorous string of aftershocks that continued to rattle us several times per hour for the first day or two. The motivations for doing this field response can be categorized into two broad efforts. Number one, adding to our knowledge of how coseismic ruptures look and behave. That spawns its own whole host of science questions. But also doing a post-mortem to understand which faults participated and how. Did this rupture fit with our models and our expectations, or does it require a rethink? So to begin that assessment, we look at how this earthquake fits in the tectonic context. We're here in the so-called Walker Lane, the western edge of Basin and Range extension, bounding the shearing California. It actually accommodates about 25% of the San Andreas plate motion, of the plate boundary plate motion, meaning that material on the west side of this region is moving northward and material on the east side moving southward, in addition to the east-west extension. The earthquake occurred in the Mina deflection, which is a bend in that zone of lateral slip faults. You can see the change in the orientation of the faults that are mapped here. Shown on this colorful map are the aftershocks in the first 3 months. As with what you saw for the Ridgecrest earthquake, the aftershocks cluster around and align along the fault that ruptured, helping delineate its location and extent. Indeed, these ones follow the orientation of the nearby east-west oriented left slip faults. The next line of evidence is, of course, whether there is any surface rupture. A magnitude 6.5 earthquake is right on that cusp of having fully reached the surface or not. Indeed, there was plenty of surface rupture, though it was nowhere near as spectacular as those seen in the magnitude 7+ earthquakes that I've been showing you so far. We went around tracing, surveying, and measuring these subtle yet dramatic fractures, which showed evidence of just a few tens of centimeters, like less than a foot, of tectonic deformation. Here you can see the capable team of Camille Collette, Ali Pickering, Alex Haydem, and Chad Trexler, who accompanied me from both the Earthquake Science Center in the Bay Area and the Geologic Hazard Science Center in Colorado. We were just one of several teams that converged to contribute mapping and measurement of this vast array of ground ruptures from this earthquake. One of the best ways to see the full scope of ground deformation is from a high vantage point. So we sent up an unoccupied aerial vehicle, UAV, or more commonly known as drones, in our case a quadcopter, 4 rotors on each side, to do comprehensive photography, imaging, and mapping of the epicentral fault zone of this earthquake. These UAV surveys image the ground at 1 centimeter per pixel resolution. And we use the varying vantage points to reconstruct a detailed 3D terrain model using a process called structure from motion. The resulting data sets collected by us and others allow the teams to map ground rupture patterns in exquisite detail. You can see here in one of the images what sort of patterns we're looking at. This wide array of fractures formed above the fault zone. The results were published earlier this year, led by the Nevada Bureau of Mines and Geology, and illuminate a, surprise, surprise, somewhat enigmatic pattern of faults involved. But how unexpected was it? Well, here's the map of coseismic ruptures, plotted along with the location of the epicenter, and in black, previously mapped quaternary active faults from that Q faults database. While only a fraction of the red and pink surface ruptures from this earthquake follow previously mapped faults, here and here, for example, their configuration suggests that the faults were obscured by sedimentary cover and burial, not that they were newly formed structures. I'll take you on a quick tour of what some of these tiny fault ruptures looked like. In the far east, Seth D. from the Nevada Bureau of Mines and Geology is standing above one of these little fractures, a few centimeters wide, that runs off into the distance, but it actually lies along the trace of this large fault that you can see in the background, offsetting this ancient lava flow from its counterpart over here. So we're seeing activation of big, well-known bedrock faults in a minor way from this earthquake. Similarly, deep in the sedimentary basin over here, you can see this array of fractures running through the desert gravel. There's measurable offset across these, and it lines up in between the projections of two well-known and recognized faults on either side of the sedimentary basin, suggesting that this is an expression of the continuation of that fault. On the west side, we can see this small fracture that runs along the base of a larger, or it's frankly pretty subtle unless you're a geomorphologist, but there's a step in the landscape that's recognizable here as something that must have been tectonic. Sure enough, this rupture runs right along the base of that. So a lot of this is in fact rupturing faults that were previously identified in the landscape. Here, in this main zone of fractures, Alex Hayden is celebrating the discovery of the main fault that really ruptured to produce this earthquake. It's still not that impressive. Well, zooming into that western domain, we can see what having this low altitude aerial drone imagery does for our ability to see and map the rupture in detail. Ongoing investigations are evaluating just how much of this faulting occurred along faults that could have been previously recognized, and are hunting for more evidence of such features in the vicinity. When we simplify the surface rupture interpretation and add in mapped aftershock epicenters to highlight where the deeper portions of the fault that ruptured are, we get a clearer picture of the structure behind this earthquake rupture. The portion of the fault that broke was around 30 kilometers long from east to west, following the buried continuation of the previously identified Candelaria fault. While rupture on that fault didn't reach the surface, slip along it torqued these other intersecting north-south faults and made them tear open with minor offset, as we saw. Overall, the faults activated in this earthquake appear to represent a microcosm of what we expected from the regional tectonics within the minor deflection of the Walker Lane. While it ruptured newly mapped faults, the pattern of faulting is entirely consistent with how we would have expected an earthquake in this region to operate. And the particular configuration of this one shows us ways in which the faults that we have already mapped may link up. This brings us to the present day, and we can revisit our confounded colleague Chad here to answer some of his questions. What do we learn from mapping all these fractures? Well, each earthquake rupture that's mapped reveals more to us about how seismic slip propagates along a fault system, linking tectonic structures. These, in turn, inform simulations of the physical process so that we can understand better the mechanisms and the theory behind how earthquake ruptures really work. They also calibrate how to interpret the magnitude of past events when they're preserved in the landscape so that we can interpret earthquakes beyond our instrumental records. Why do so many large earthquakes keep happening outside the zone of highest shaking probability? Well, while the San Andreas and nearby faults move fastest in geologic time, which means in human time that earthquakes recur most frequently, the deforming part of the continent is wide and diffuse, hosting an abundant set of faults, each one capable of producing large earthquakes. Even if each one produces an earthquake rarely, this huge collection of faults will collectively produce a large number of earthquakes, which is why most of the ones that we've experienced in the last century have come from off of the San Andreas. How have recent earthquakes informed our expectations of future seismic events? Well, because each earthquake is different, new earthquakes can surprise us. By assimilating all these examples of modern ruptures and fleshing out the longer-term history of earthquakes through mapping and excavation, we have an ever-improving handle on which earthquakes may occur in the future, where they will strike, and how big they may grow to be. Understanding the tectonics through studies of past earthquakes and old bedrock faults is critical to understanding how contemporary, meaning future, ruptures will navigate through the fault system, allowing us to foresee where and how large are the earthquakes that society will face. With that, I'd like to thank you all for listening, and I'd be glad to answer any of your burning questions about these earthquakes, other earthquakes, and earthquake geology. Thank you.
Awesome. Thank you so much, Austin. It's a fascinating lecture. Hard to imagine, 2020 was such a long year, but seeing how many large events happened in the Western U.S. in such a short time span. Yeah, great stuff. So we already have some really good questions from the audience. So we're gonna open up to our Q&A portion of the lecture. So I've been keeping an eye on some of the questions that have been coming through. And just as a reminder, if you would like to ask a question, remember to click that Q&A chat window. Look for the question mark icon on the upper right-hand corner of your screen. And if you're on a mobile device or an iPad, you can click on the question mark icon, which is also located on the upper right-hand corner of the screen, and submit your question there. So our first question of the night is from Januka, who asks, are any of the 65% of the unmapped faults in the Ridgecrest new, i.e. not pre-existing?
Could you repeat the first part of it? How are any?
Yes, if any of the 65% of the unmapped faults in Ridgecrest are new.
That's right. So only 35% of them were in the Quaternary faults database already. An additional 35% of what we saw rupture in 2019 were in fact recognizable features that had simply been, I wouldn't say overlooked. The desert is vast, and there haven't necessarily been studies of every square foot of the desert so far. So what this earthquake sort of inspired researchers to do was go back and really interrogate, were there in fact features that could have been recognized before if we'd had dedicated studies here. And so what they found is that additional 35% were. There is in fact a remaining sort of third of the ruptures that had no expression previously. That doesn't mean that they're, strictly speaking, new faults. The Mojave Desert is characterized by deep sedimentary basins and just piles and piles of gravel shed off the mountains. And over time, those will tend to bury faults. And so it's again this competition between, are the faults keeping up with forming linear features and escarpments, or are they getting washed over, washed away, and buried by sediments? And that's a perpetual challenge that we face studying the faults geomorphically.
Great, thank you. And our second question of the night, about earthquake experiences. So someone's asking if they're hypothetically standing in a field along a fault when an earthquake happens, what do they see? Does the offset motion happen in the blink of an eye or over 2 seconds?
This is a fabulous question, and I'm sure one that fascinates all of my colleagues. We all, as we're standing out there looking at these fresh scarps that formed just the day before, we're all imagining what would it have been like to see this process unfolding. There are a small number of people around the planet who have witnessed this happen, and they've been lucky enough to, and they've shared their experiences. And we also know from the physics of the process sort of what it would look like. So the rupture tip itself, as we saw in that simulation, it moves at, let's say, about 1 kilometer per second, maybe faster. And so that's pretty quick. If you're standing on the ground looking towards a fault, the tip of that opening crack is going to sort of zip by across your field of view in a matter of a couple seconds. The actual, we would call it the rise time, the time that it takes the fault to then move, is going to be an additional couple of seconds. The slip velocity of the fault sort of catches up. There is one video from an earthquake in Taiwan a few years ago that captures this process happening. It was a closed circuit TV camera outside of a shop under which a fault ruptured. You don't exactly see the fault break, but you can see over the course of basically 1 or 2 seconds, the house rides up over the street and then sort of parks itself there. And so you would see the crack zipping open, and then you would see over the course of just 1 to 2 seconds that scarp form. In the midst of this, of course, you would be experiencing very violent shaking, because the shaking is produced by that elastic motion of the ground. And so the strongest shaking you experience is probably going to come right as the main rupture passes.
Awesome, thank you. And our next question is about terminology. asking, when did the term unzipped for faulting begin being used?
I wouldn't necessarily say it's a technical term. I use it as a helpful analogy to the process that sort of unfolds over time laterally. And so I think that process of breaking down the frictional bonds across the fault over time as it moves along is really analogous to unzipping something, sort of breaking the bond between two sides of it so that it can move independently.
Thank you. And our next question from an audience member, they're asking, what created the Mina bend?
Well, that's a good question. Going back, so one of the diagrams, there's my slides here. Let me jump back if I can to our diagram here. I glossed right over this, but a model that was sort of proposed in 2005 for why this is happening. What you got is, again, that Pacific plate boundary motion, where in the west, stuff is moving northwest, and in the east, stuff is moving southeast. So these long faults that are oriented to the northwest are strike-slip faults that are accommodating that sideways motion. What's happening in the Mina deflection is that for some reason, the plate boundary motion, that strike-slip, gets transferred out into the basin. That may be because there are more faults available over here, and it's starting to sort of co-opt the extensional faults and start to move them laterally. That's one part of what may be happening. And so in the middle there's this little zone of material that is somehow having to accommodate a bit of a gap in the motion. If you're moving this stuff southward and this stuff northward, you're opening a bit of a gap here. The model that's proposed is that the rocks in the middle are essentially pinned between these two sides of a wider fault zone, and thus sort of pinned and rotating like ball bearings, essentially. What that means is that in between those, you have faults with this opposite left lateral sense of motion. And quite truly, that is exactly what we're seeing here. There's a stack of these left lateral faults in the middle of the right lateral faults. And so you can imagine that the two sides of the Mina deflection are sort of pinned, and as this moves downward and this moves northward, it rotates the intervening bit like dominoes. That means that when an earthquake happens, it's navigating its way among this evolving set of faults that are rotating through time, which may be why we see those surface ruptures that are not exactly aligned with the east-west orientation of these other faults.
Got it. Thanks, Austin. Our next question is from Bob, who asks, is the Walker Lane a possible future San Andreas trace, i.e. a replacement for the San Andreas fault?
It's another really great question, and basically a subject of ongoing hypothesizing and research. And there is a general consensus that there's a massive shear zone there that accommodates a quarter of the plate boundary motion. And when you look at it in map view, here's a small version. I can maybe jump us up to the bigger regional picture here. You can see that, number one, it's the most active part of our big deforming belt, right? All the historic earthquakes have happened basically along this line that extends down to the rifting Gulf of California. And so essentially what we're seeing in Southern California is the northward propagation of this rift that has separated Baja from mainland Mexico. That same shear extends up through the Mojave Desert and then into the very western edge of this extensional province. And so there is an alignment of things here that is growing. These faults are maturing with every one of these earthquakes. As you can see, the faults are linking together, right? They're forming longer faults as they produce this. And so over the next millions of years, 5 to 10 million years, we probably will start to see reconfiguration of the plate boundary that's more accommodating of a simpler, straighter boundary. Not in our lifetimes.
Good to know, thank you. And our next question is from Stephen, who asks, is the overall goal to predict earthquakes or just to understand their cause and effect better?
It's long been a goal from the public and a scientific perspective to wish that we could predict earthquakes, but there are so many complexities and variables within the system that it does seem a pretty unattainable goal. In the meantime, what we do is we try to forecast the suite of earthquakes that may occur so that we have a better handle, so that we're not surprised anymore when big ones happen. When we live on an active plate boundary, earthquakes are always going to happen, and the strategies for dealing with them, there are much more effective strategies than predicting earthquakes in advance. If you were able to predict an earthquake, you would still have to deal with that. What would you do? You have to evacuate a city? What do you? There are some real challenges conceptually with dealing with a disaster that way, when there are other measures you can take to cope more robustly with an earthquake and build infrastructure and resilient communities that can withstand them, in the same way basically that we withstand big rainstorms.
Thank you. And our next question is from John, who asked, drones can map details after the event, and aerial mapping showed faults that could have been found. But what is the value of using these methods much more extensively to map previously unknown faults?
Well, that's our favorite topic as geomorphologists and earthquake geologists. We would love to have high resolution imaging and topography of every corner of the planet. And it is in fact a big effort of what we do. USGS has a big program to capture high resolution LiDAR, laser imaging and topography, and to make it freely available for researchers and the public to use. Some of the high resolution topography that we have, some of the earliest high resolution topography that was produced was actually in pursuit of before event fault line data. So looking at specifically the San Andreas fault, other big regional faults that we knew to be threats. The first LiDAR data sets were really captured in stretches along those and have already been put to use, being measuring before and after changes to the terrain from some of these big earthquakes. They give us a really detailed picture of exactly not just where the fault traces are, but the whole deformation field, because it's not just these single cracks in the ground. There's warping that extends over a longer region, and that gives us also a better sense of both how large the earthquake was and sort of what structures, what subterranean structures were involved in producing that. So there's great value in high resolution topography. We're always in pursuit of more.
Gotcha. And gotta have a really good question about earthquake preparedness in general. What actionable tasks based on these new learnings can one take living in the highly populated Bay Area, California?
It's a really great question. So a lot of the research that I discussed here, the implications based on fault crossings, all this fault rupture stuff, the applications of these are largely with larger infrastructure and sort of city planning issues. As individuals, you're probably going to be more concerned with the shaking itself than with where the faults rupture. But of course, the shaking is dictated by how long the fault rupture is, right? So in the Bay Area, for example, the Hayward Fault is this massive threat to the East Bay and really the entire region. The distribution of shaking from the eventual earthquake that it will produce is going to depend on exactly how much of that fault ruptures. And so understanding this distribution of, in any given earthquake, how much of the fault ruptures, or are there particular features that halt the rupture from propagating, those are going to control the distribution of shaking, and thus sort of how cities plan for and budget and insurance companies and infrastructure utility companies and agencies deal with those things. As an individual, living in earthquake country, the reality is always just that an earthquake could hit at any time, and it's the reality that we live with. And so getting yourself prepared, making a plan with your community, anticipating the effects, the lingering effects that a large damaging earthquake is going to have in the region. The USGS a few years ago produced this massive report, the Haywired report. You can look that up, and it has a rather daunting set of prognoses about what may happen when the earthquake occurs, but that's really the first step to starting to get control of it and to anticipate what's going to happen and be able to prepare yourself for it. Because in reality, most people are going to survive, live through, and recover from these earthquakes. And there are many societies around the world, think of Japan and Chile, that deal with earthquakes very well. They take them in stride. They deal with them like they're just another rainstorm, which, by the way, in California, rainstorms are their own disasters. But we have, yeah. The recommendation is get prepared. There are plenty of resources. Look into the Haywired report. And I would emphasize the importance of preparing within your community and making sure that there are people around you who are also aware so that the problems don't spiral out of control. The pandemic has taught us a lot about that.
Absolutely, thank you. And I'll put a link to that Haywired report in the chat window as well for that user. And our next question comes from Anne. Anne is asking if the continental extension in Montana is any way related to the California-Nevada movements.
That's right. My talk is focused on this sort of southwest corner of the U.S. But if we jump back, let's just move that. What you can see here is that we're basically looking at one big system. So the extensional province that spans the entire state of Nevada and reaches into Utah. The Wasatch Fault is the famous eastern boundary of that. It's highly active. Those faults project northward. They cross the volcanic Snake River Plain in Idaho, and they extend up into northern Idaho. This was actually the site of one of those other big earthquakes last year, as well as another large earthquake in 1983. So Idaho is definitely also earthquake country, as is southern Montana. And these are indeed parts of essentially the same fault system. Technically speaking, there are complexities introduced because in the north, we have the Cascadia subduction zone. There's convergence where the Juan de Fuca plate here is colliding with North America and pushing back inward. You can see that in the velocities as the continent is getting scrunched up here. So some transition happens in this zone around basically within Oregon, but overall, it's part of the same extensional belt. You muted, Will.
Oh, sorry about that. I didn't want my typing to get in the way. So our next question is asking, in the example that you presented, the surface ruptures are complex. Could that be termed distributed faulting?
Yeah, there are a lot of pardon me while I turn my lights on. The short answer is yes. We would term that distributed faulting. The exact relationship of all those different fractures with the sort of main fault that was seismogenic that produced the earthquake is essentially still under investigation. We're looking at the questions of exactly what those smaller fractures represent. There's some manifestation of deformation around the tip or the edge of a major fault, and so yes.
Great. And we have time. We're going to ask a few more questions and wrap up our Q&A portion. So our second to last question is from Jeff, who's asking, did the plate motion networks provide any foresight for these recent earthquakes?
Yeah, so none of these earthquakes have been preceded by any sort of recognizable or reliable precursor. In fact, we've really never found any reliable precursors. Certainly some earthquakes have foreshocks that happen months in advance, but there's really no way of knowing whether any given earthquake is going to be a foreshock or not. Only 5% of earthquakes end up being foreshocks, which is a very small fraction of them. No precursory geodetic signals have been identified for any of these. So that's basically it. Other than simply the notion that this is a deforming region and we do expect earthquakes there, that's what we can tell you. Another feature that's worth noting is the alignment of ruptures that has happened. There is significance to this belt of higher deformation, and it is where an area where we expect earthquakes to be more likely. So we can see that over time, all these successive earthquakes have started filling in the gaps. They're less likely, they don't necessarily happen in the same place or right next to each other, although there are examples of that as well. But you can see lots of filling in the gaps along this belt. It's almost complete.
Got it, thank you. And our last question of the night is from Bill, who's asking, can satellite imaging help discover these tiny, previously unknown features, or are you limited to drone imaging and field studies? If the former, is USGS involved in the Surface Biology and Geology Decadal Survey?
Yeah, so first of all, yes, for identifying prior geomorphic landforms and prior evidence of faulting, satellite imaging is one of the key things that we use. The features that we're looking for and that are generally recognizable are captured very well by orbiting satellites, which have imaging resolutions of something like 30 centimeters to a meter at their highest. Features like we saw in the 2020, this Monte Cristo Range earthquake, are so small that it's very unclear to us whether those would be measured in the future. So if we look back with hindsight, even 10 years hence, would we recognize that there had been an earthquake rupture here? These little fractures that are only a few centimeters across get filled in really fast. So again, we're talking about this earthquake was right on that cusp between earthquakes that get lost in the geologic record and earthquakes that are preserved. And so the exact boundary there is something we're really trying to dig into. So collecting satellite data, however, is a really critical way that we have of identifying any sort of active faults and making measurements across them. The specifics of the program, the decadal surveys, I'm going to have to deflect that specifically, but there are a number of campaigns, data collection efforts, data dissemination, and generation that the USGS is involved in terms of high-resolution terrain and topography.
Thank you. I'm sorry, I'm going to sneak in one more question because it's a really good question. I'm curious to see what the answer. So someone's asking, how do these unmapped distributed fault traces that were only mapped after the earthquake affect recommendations for fault setbacks or fault avoidance zones?
Yeah, so that's a great question. While we cannot rely on being able to map those for past earthquakes because they're just so small, there are a couple of things that we're looking to do. One of them is to identify whether there are any broader signatures of them. So maybe the discrete fractures don't get preserved, but maybe there are longer wavelength warping of the landforms or other things that could be recognizable in past events or for prior events before we recorded them. But the other thing is that, as I said, each of these new earthquakes that happens is one of the key ways that we get new data about how these ruptures occur. And so that's why it's so important to get out to the field rapidly and collect as detailed surveys as possible so that we understand the distribution of this deformation, because these data sets from the historic ruptures are what go into this new emerging field of probabilistic fault displacement hazard analysis. And this is used by, especially for infrastructure, for highly vulnerable or highly important facilities, nuclear plants, other things of that nature. They're really interested in where exactly the ground is going to deform and disrupt their infrastructure and lifelines. And so mapping out the distribution of all these little fractures is really critical to getting it right when we build things that have to cross the fault. Whereas houses and buildings can be set back from the fault, roads, railroads, pipelines can't be. So we have to learn how to build across them.
Thank you for answering that. And again, that's all the time we can have for questions this evening. I want to thank you again, Austin, for the talk today. Super fascinating stuff, and just for fielding all of our questions. Really great questions from the audience. And thank you again to out there, everyone in the virtual world, for joining us tonight. And just a reminder, Austin's lecture will be available later for on-demand viewing on our website at usgs.gov/PLS. And again, we hope that we see you next month on June 24th at same time, 7 p.m. Pacific, for Carolyn Dreger's lecture on Mount St. Helens. Until then, have a great night. Thank you all for joining us.